Problem 4. Find all positive integers n such that n times 2 to the n plus 1 is a square. It's not obvious what to do to start with, so a good idea might be to try some small numbers and see if they work. So I'm going to make a table. I'm going to try some values of n, and for each of them I'm going to work out 2 to the n, and then I'll work out n times 2 to the n plus 1. So I'll start by taking n is 1, and in that case 2 to the 1 is 2, and 1 times 2 plus 1 is 3. And that's not a square. What if n is 2? If n is 2, then 2 to the 2 is 4. 2 times 4 plus 1 is 8 plus 1, which is 9, and that is a square. If n is 3, 2 to the 3 is 8, and then 3 times 8 is 24, plus 1 is 25, also a square. So we found 2. What if n is 4? If n is 4, then 2 to the n is 16. 4 times 16 is 64, plus 1 is 65, which is not a square. If n is 5, then 2 to the n is 32. 5 times 32 is 160. That plus 1 is 161. Also not a square. As we keep going doing this, the numbers are going to get kind of large kind of quickly. So there's a limit to how many examples we can reasonably get. But if we push on a bit, we'll just find no more squares. So we might come to believe that maybe 9 and 25, which we get when n is 2 or 3, are the only examples. So we'll go and try to prove that now. OK, so let's say that n times 2 to the n plus 1 is a square. We can call it m squared. A natural thing to do from here is to take the 1 to the other side. So n times 2 to the n is m squared minus 1. And then we can use the difference of squares factorization on that. So that's equal to m plus 1 times m minus 1. Now we see something interesting. So on the left here, we have a large power of 2, at least if n is large. On the right, we have these two terms that differ by 2. They can, of course, both be even if m is odd, but it's very hard for them both to have lots of 2's in. So if one of them is a multiple of 4, the other one will differ by 2 from it, and so won't be a multiple of 4. It'll be even, but it'll only have one factor of 2. Therefore, all but one of these factors of 2 on the left have to be in one or other of these terms. In other words, either we have m plus 1 is a multiple of 2 to the n minus 1, or, alternatively, we have m minus 1 is a multiple of 2 to the n minus 1. We should consider each of these cases in turn. OK, I'm going to do the second case first, as it turns out to be ever so slightly easier. So if m minus 1 is equal to a times 2 to the n minus 1, I can substitute into this middle formula here, and what I get is that n times 2 to the n is equal to m plus 1 times a times 2 to the n minus 1. And then I can cancel all the 2's from the right-hand side with most of the 2's on the left-hand side, and I get 2n equals a times m plus 1. Now we're in an interesting situation. The fact that 2n is equal to a times m plus 1 means in particular that 2n is greater than or equal to m plus 1. But this formula here tells us that m plus 1, which is of course bigger than m minus 1, is greater than or equal to 2 to the n minus 1. That tells us in total that 2 times n is greater than or equal to 2 to the n minus 1. And that's an inequality that's only valid for a very small number of values of n. As soon as n gets large, that'll no longer be the case. And you can go and look at some numbers, and you can check that this is in fact only true if n is less than or equal to 4. The remaining case on the left is pretty similar, but slightly more unpleasant to write down. I'll start by doing the same thing. So if n plus 1 is equal to a times 2 to the n minus 1, I'll substitute that into the middle formula here, and I get that n times 2 to the n is equal this time to a 2 to the n minus 1 times m minus 1. And I can cancel almost all the 2's from the left and get that 2n is equal to a times m minus 1. My aim is again to generate some inequalities here. So what am I going to do? This time I'm going to say that 2n is greater than or equal to m minus 1 as a result of this. And then I want to use this, but unfortunately this involves m plus 1, and what I've got here is m minus 1. So I'm going to write that as m plus 1 minus 2. And then I'll use that this tells me that m plus 1 minus 2 is greater than or equal to 2 to the n minus 1, because m plus 1 is equal to a times 2 to the n minus 1 minus 2 from this minus 2 here. Again, this is an inequality that can only hold for a very small number of values of n. So as n gets large, the left-hand side here will get large much more slowly than the right-hand side here. And in fact, again, you can check that this holds only when n is less than or equal to 4. So the conclusion is, in both cases, the possible n that give you a square are at most 4. So the table of values I did at the beginning gives you the only numbers that are squares, namely 9 and 25.